I think it's fine now. Yes. So elastic material is modeled using Young's modulus, Poisson's ratio, and density. Like this has already been discussed, right? But steel is an plastic material, and then I also discussed after you cross this elastic limit or yield limit, then there is plasticity, right? This AD is plastic strain. If you go from B to C, then unload, you will get AD. This will be your, when it comes, it will not come back to its own position, exact position, initial position. It will come to D. So AD will be the irrecoverable plastic strain. Okay. So there is, in concrete, once you cross the yield limit, within very soon you'll see hardening, softening, and damage. But steel is a ductile material, so it's something like this: elastic limit, then you go hardening. At this point, it's called necking. Then there is softening, and then there is rupture. What it means, I'll explain. So, what is elastic limit? It is when hook up to this elastic limit epsilon y, Hooke's law is valid. Following that, there will be there will be plastic strains. But at the necking, there will be
So,
strain. Any questions?
someone asked for class on WhatsApp.
Tell them it's already going on.
On WhatsApp,
Yes, the link is already in your email. So
maybe he don't know about the email.
It's already shared in the Google Calendar.
yes. So what? So after yield limit or yield elastic limit, plastic strains are there. If you unload, it will not come back to its own position. But what happens in necking? In necking, when you pull this, say you are doing tensile stress. Yes. So at necking, there is strain localization at this point. When you pull it, it becomes like its area of cross section decreases and strain gets localized here. This is called necking. And then there is softening. At rupture, it completely breaks. It completely breaks. So it's a relatively ductile failure mechanism as compared to concrete or masonry. So in this, we have a concept of engineering stress and true stress. So engineering stress is very simple, which we have been using. That is force per unit area. We have applying a force F. The initial cross-sectional area is A naught. So force per unit area. That is engineering stress. Engineering strain, it is a change in dimension by initial dimension. Change in length by initial length. So this is called engineering and engineering stress and strain. But what happens actually when you apply the force or stretch this specimen, the length increases, okay, but the area of cross section, it decreases, so that volume remains constant. Okay, so this engineering stress is F divided by initial area. However, as you increase F or as you apply F, A gets small and small. So F divided by A, that will be the true stress. Similarly, U by L naught, it is engineering stress. But the when you see U by L, suppose you are increasing F, initially it was L naught, then it increased to L. Now you are further giving some increment. So change in length is U, and L is continuously changing. So that is true strain for you. So what is the relation between engineering stress and true stress? So engineering true stress is equal to natural log of 1 plus engineering strain. Sorry, true strain is equal to ln 1 plus engineering strain. So what happens? This value gets reduced, right? Ln of 1 plus something. So if you compare engineering stress in one column and corresponding to that true stress, you will see true stress, true engineering strain in one column corresponding to that true strain. You will see true strain is less than engineering strain. Now, how do we calculate engineering stress or true stress from engineering stress? True stress is equal to engineering stress multiplied by 1 plus engineering strain. So this value goes up, right? Because it's 1 plus something. And you're multiplying that factor to engineering stress. So true stress is greater than engineering stress. So if you see up to elastic limit, you can also use this formula, but there will be very small difference. Post elastic limit to necking, you see the engineering, the true stress, it gets increased. Okay, so this is the relation. Now, how to derive these? You can find them in any book of plasticity. These are very simple. You just have to use the concept that A gets reduced and L as L increases, and the volume remains constant. But once necking starts, that is, strain localization takes place. How do we define true stress and true strain? So there is one way that says you just vary it linearly from necking to rupture. You have this data, you have this data, you just vary it linearly. So how they have done it? See, this data you already have. How to calculate this data? True failure or true rupture strain is equal to similar formula, ln 1 plus engineering strain at rupture or failure. How to calculate true failure stress? Force at failure divided by area at failure. Once your specimen breaks, you calculate the area and you know the force, you calculate this. So this is one method. You have this value, you compute this value using these two formula, and you vary it linearly. This is one. Another is linear variation, but you vary it like at this point you draw tangent. How to draw that? This is the relation. Sigma equals to A epsilon plus B. Here A equals to true ultimate true stress, and B equals to ultimate true stress minus multiplied by 1 minus ultimate true strain. Okay, so this is all relations are taken from some papers. Okay, so it's just the tangent. You don't have this data, you have only this data, right? Sigma u epsilon u. This is the engineering this yes, this is the engineering stress and strain corresponding to necking. But here you are using true stress and true strain corresponding to necking. That you know how to obtain it, right? These two values. Then at necking till failure, you vary it linearly, but this is tangent to the necking point. So these are the formula, right? This is very simple. Following that, there is one more non-linear relation. You can use that one also. Wait, yes. So this says sigma, how sigma varies from this to this, true strain, how true strain varies from necking to rupture, this formula. Necking true strain divided by necking true stress divided by necking true strain raised to necking true strain multiplied by your epsilon, which is from this to this raised to necking true strain. Now where did I get this formula? I have the paper. This is by Linz. No, yes. This is by Ling, 1996. He has published this in 1996. This is the
Can you
equation.
send it?
Yes, yes,
Can you
I'll
share
upload
it
it.
with us?
Yes, 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 I'll upload it. So this is the paper. Like if you want to use it in your work, you have to cite this paper. Okay. This is after making. Then we have to input yield stress versus plastic strain. How yield stress, you know the yield stress, yield true stress, right? Which you have. How to get the plastic strain? Sigma true, that is true strain minus sigma y. Sigma y is elastic strain. Sigma y is elastic strain. So you multiply the true strain, but you subtract the true strain by this value, you'll get the plastic strain. Plastic strain equals to true strain minus elastic strain. Finished. Your curve will look like something like this, because up to this point there is no plastic strain, so it will be 0, right? Corresponding to sigma y, plastic strain will be 0. See, corresponding to sigma y, plastic strain will be 0. Then it varies like this. So whatever I discussed till now, it is only for monotonic loading. Okay, it is only for monotonic loading. That is, you are just applying a load, not for cyclic loading or fatigue. For that, something else has to be done. We have to. There are different methods which can be used that will be discussed in further sessions. So anything up to now? There is actually a lot of literature on steel. Sorry. So I'll share everything. This is for uniaxial. For cyclic loading also, we'll discuss it. So let me go to the data. I think I should go to the presentation again. So this is some data which I'm having. This is stress versus strain. Okay. So this value is your necking, and then we have used linear relation rupture. This value is your yield, engineering stress and strain. Up to this, the behavior is elastic. You'll see up to this, plastic strain is 0. Okay. And this is Young's modulus. This is area at failure. Yield limit. This is yield limit. Yield, strain, necking, stress, necking, strain. Okay. So see, engineering stress strain. Okay. Then true stress, true strain, true stress. This is the formula for true stress. This is the formula for true strain. They have been used here. See, ln 1 plus engineering stress. Engineering ln 1 plus engineering strain. Sorry. Here, engineering stress multiplied by 1 plus engineering strain. This has been used. Okay. Then how do you calculate the plastic strain? Strain, true strain minus elastic strain. B2 is the Young's modulus. So we'll input this data. This data will be input. This J and K will be input as material properties. Okay. So model again of being Be 500, 500. Again, millimeter, and to be property. You go steel. Density 1800 kilogram per meter cube, but I'm using Newton, millimeter, and seconds. So you have to, like, this has already been told. Elasticity, Poisson's ratio, 0.3. And we go Young's modulus. This is Newton per millimeter square. Okay. Then we go plastic, simple plastic. Okay. Here it's important. There are various uh, hardening models. If you are using monotonic loading, doesn't matter which one you use. No effect. It doesn't have any effect. But if you are using cyclic loading, then we have to use combine. I'll also show you how to do this. We'll probably use this one, parameters, but this will be discussed in the next class. So isotropic, then we go with yield stress here. So here, copy. Fine. Plastic strain starts from 0, then increases. See, this is corresponding to rupture, this is corresponding to necking. We have assumed a linear relationship. Done. Then we'll create a section. We'll assign it to beam like we have been doing. Okay, go to assembly, instantiate it. Then we go to step. Now we can do, okay, how do we do it? Let's try something different today. Let's keep it. Step 1, I'll name it as pre-compression. Add a few zeros here. I think it should be fine. 3.1. Let's see if there is any problem. We can fix it. This is first step. Then I'll create another step. Loading. Maybe one. Keep it on implementation. Maybe like this. Right. Then we'll do like this. Go to load. Firstly, create the boundary condition. And fix it. Done. It's fixed. Right. This one. Then I'll go to create load. Pressure. Initially, I'll go with 0. Okay. Let's go with 1. Okay. But then move it to left. This is your pre-compression. I'll compress it. Okay. But initially, no pre-compression. Fine. We'll create one more. This time I'll create, sorry, just keep it as it is. I'll create one more. This is boundary condition. Initially, it has to be fixed initially. I'll create one more in loading step, maybe displacement. Click here, okay, like this. So maybe we'll fix. No, do nothing. Just put any value. I think we should give high value here, right? Let's start with 50 or 100 maybe. 100 millimeter displacement. Okay, this amplitude ramp, keep it as it is. No, we should keep it -100. Okay, let's go to load again. Create. We can also, I'll show you to create gravity load. Okay, create gravity in initial step. No, in pre-compression. Let's create gravity here. And amplitude is ramp. What is only component 2, right? What is it? -9.81. Is it correct? Anyone?
Yes.
Yes.
No, it's not correct. It's 9.11 meter per second square. But I have to put millimeter because I'm using millimeter as my unit of length. So I'll write it 981.
981.
Yes. 981 is my component. Let's see. Whole model. It's fine. Or you can also select this like this. Okay. Done. This is the gravity. Let's keep it as it is. Or we can maybe put it like this. Whatever we want. Let's ignore both of them initially. So what we have now? No loading, nothing. Fixed initially, then some displacement here. Okay. After load, I'll go to interaction. I want to do something. What I want to do, I want to create a reference point, but first I will create a datum here, midway between 2 points. This is my datum point. Then I'll create a reference point. Then I'll use rigid body. What rigid body does is I want reaction. So it will sum up the reactions at all the nodes and add them corresponding to this node. You can type in anything. I have already discussed that yesterday. Done. Done. Okay. Go to step again. Field output. It will. It's fine. Just keep it as it is. Okay. No issues with it. What I wanted, I want a history output in pre-compression. Starting from pre-compression. But I have to close this first and ask for create reference point. I want history output force corresponding to this reference point. So rigid body constraint will sum up the reactions at all the nodes and transfer to this point. I want another set displacement nodes. Okay. Like this. Then I go to history output. Probably maybe say 0.1. Set RP forces. Done. Right. Another history output. This set displacement nodes. Okay. I just want something X units of time 0.05. X units of time 0.05. Okay. Now load is done. Mesh, create bar, seed, 25 maybe. Relatively finer. No, it's more fine. Let's go with 50 because I don't want to waste the time unnecessarily. So I'm doing here what you should do. You should try to do mesh convergence and then see the results. Job. No, 8 point. No, this. What actually I want to see is firstly I want to see at what displacement or at what load the beam fails. It will get completed and just because this right. This will be good. That's fine. These warnings are not important. Incorrect. Let me see. Go to this. So it says that like here what you can do is you can remove the constraint here and add it to reference point. This will get disappeared, but it doesn't matter. Okay. Why is 0. So I went for 100 right here. Is there any plastic strain? Yes, there is. So it has probably failed. RF2, that is the vertical reaction. No, not yet, right? It has not failed. You can see linear and there is some hardening. So what we'll do is probably maybe increase this to 200. Submit it again. Next, what I want to do, I'll show you. Here, which fixed, only vertical loading is there in the form of displacement at this point. Sometimes we also applied pressure. That was a force control loading. This is displacement. So there is no pre-compression or no gravity force as of now. Let's see, I just will have a look at the interaction if there is any issue with the interaction or not. It's fine. Not completed, right? Plastic strain is there. What I want here is R2. See, elastic limit, hardening, but no failure. Suppose you steel beam, it will not fail easily. Let's see, 400 or 500 maybe. Let it get completed. Okay, let it get completed. I want to see failure, then I'll show you some things once I see like very much hardening or a lot of softening. Still relatively fast. We can study two things from here. Firstly, we have this rectangular section. How about we replace it with T section? You can do it, right? Or how about we replace it with I section or L section? Yeah, 500 cross 500, but just the section is different. And see what is its capacity. It's showing some displacement now. See, yes. But I don't think it has failed yet. It's 484. Let's see. You also saw the force displacement response for concrete, right? It's still hardening, right? I don't know what to do now. Maybe 1000. For concrete, you could see the cost brittle nature, and for steel, you can also see the ductile nature. Let's see what happens with 1000. Hopefully, it will fail. I think it should fail, or at least there should be softening, because I want to see the capacity, the ultimate capacity of the beam. You can now what you can do is you can replace, as I told you, you can replace it with I section. So keep it 500 by 500. Keep the thickness as 100. So it will be 100 like this and 100 like this. Then you can replace it with T section. So this is 500. The thickness will be 100 here. So you will maybe 200 from this side in the middle. It will be like this. That will be your T. L section I told you 100 again. I section again 100 and thickness. Then see, once it should fail, we will see at what displacement it fails. Then you can compare the sections. And also, once you compare the sections, you'll we can maybe do it as a part of a project. We can see at for different sections what is the capacity, because the material required to make this beam is large, right? If we have T section, I section, or L section, it's relatively small. And if the same material gives you close enough displacement or force capacity, then you should go with the material having the section having lowest material requirements. But also you should also check for stability. That is the later part. Let's leave stability as of now. It's still not failed as far as I think. It is still not failed. See, nothing is happening. It's just going, right? What can we do now? Maybe last try. No, it's a beam is actually very huge also. Wait, we'll do something like this. We'll check the results. Maybe S22, S33649, right? And probably some damage is there, right? Some damage is there, so it will fail soon. Maybe for 2000. It's a little bit boring, but it should fail for this. If it didn't, then I'll proceed further and show you something else. While you make the steel, you can also have residual stresses while manufacturing the steel. So there are like, how steel is manufactured. Like it can be additive or subtractive. So subtractive, you have a lot of steel and you cut it into parts and make your required members. Additive is, the geometry, you'll start from zero and start the 3D printing of steel. So that is also one methodology. You can have residual stresses in those cases in steel. So if you know the residual stress distribution, you can also model those. But let's see who has joined. No one, no one outside of any. So this was for monotonic loading, right? For cyclic loading, we don't have to define. We cannot define like this, because I'll discuss kinematic and isotropic hardening. Then we have to define here combined, and the better way is parameters. These parameters, obviously, they are what they are. They are taken from the literature. I'll also share the papers with you. So leave this, keep isotropic as it is, or maybe cancel just here. This got completed. I hope we see some signs of failure now. No, nothing. Okay, anyway, let's keep it as it is and we'll just save it. Okay. Now what I'll do, I won't add gravity, but I'll add this load. What is this? This is the pre-compression. Maybe I'll go with, what is the, let's start with 300 megapascal. Okay, I'll go with 300 megapascal. Now 300 megapascal is pre-compression. Okay, copy this job and write 300 MPa. And submit it. Now what happens in the first step, it will start applying the pressure. Okay, once that is done, then it will apply the displacement at this point. Then you'll say, why do you want to do that? Because I think it is same, right? Yes, it is there. Because I want to see, does that affect our results? It should, but let's see by how much. It should, or maybe it wouldn't. Actually, it will. If we subject our specimen to failure, it will. It will increase the force capacity. Okay, so you have cut back. Maybe it has decreased your force capacity. There is some cutback, some failure is there, right? Let's localize something. It has caused failure, right? No, it's still not worth it. This you might be confused. See, this value is very small, right? E raised to minus 6. So don't get confused. Let it complete. Why it happened? Because I when I opened this, it was at the time 0.7, 0.7. So it got aborted. Why it got aborted? Because of the convergence issues, right? And it is definitely failing. It is definitely failing. Now, why do you think it failed? Can you tell me? Probably large value of pre-compression, right? It failed, but why do you think it failed? Any idea? Okay, let me ask. Okay, you can say, but let me first ask you, what do you like? Can you everyone say what do you do? I mean to say, are you a graduate student, postgraduate student, or PhD, MTech? Just let me know what do you study or what do you do? So, Muhammad,
What?
are you student or are you pursuing your masters or PhD? What are you currently doing?
I am civil engineering. I study master civil
Masters,
engineering.
and from where are you doing your masters?
Syria. I am from Syria.
Okay, you're from Syria. Actually, I had a friend from Syria. Uh, he had done bachelor's in Syria and then he was pursuing masters in India. And what about Leela?
Completed my master's,
Okay,
joined the job.
so you are like you're looking for PhD or job?
I have joined recently in the job
Okay, in the job. Okay, and where did you complete your masters from?
in Vizag.
Okay, what about Munirul?
I just completed my master's. I'm from Bangladesh and
Okay, you're
completed
from
my master's
Bangladesh.
from Bangladesh also.
Okay, nice, nice. Okay. Anyways, can anyone of tell you how I did it fail? You all are master student or you have done masters. So can you tell
More
me?
priest, more priestess.
No, more precious, yes, obviously. But why? What was why did it fail? Don't you think it buckled?
buckling or something.
Yes, buckling.
Yes, it buckled. You must have studied beam column buckling. So it buckled. That's why it failed. Okay. So probably a lot of pre-stress is there. We have to decrease it drastically. Maybe 30 is fine. Let's see what happens with 30. I think 30 will be okay. Let's see what happens with 30. Will it? Generally, you don't apply pre-compression. See, once I applied it pre-compression, what happened? It didn't remain like, it's not like the beam now, right? See what happens? It is initially like column, and then I apply the load. So probably this will again buckle because it now started behaving initially as a column, then you applied a load at the top. So stability failure can again be observed. This pre-compression is not generally applied for this type of loading. How you can do it? You can do one thing. You can model a similar steel wall. Okay, say you can write if you want the problem statement. You can model a steel wall. I'll send you the material properties. The dimensions of the wall should be, thickness should be 100 millimeter, length and width it should be 1000 and 1000. Okay, so it's a 1000 by 1000 wall, thickness is 100 millimeter. You can fix the bottom part of the wall. Okay, and define the reference point there, and then I showed you a rigid body constraint, and then request force and displacement from there. Okay, then what you do is you at the top of the wall you applied a horizontal loading along the length at one edge, and see how force displacement response is there, and try to fail it by increasing the load. Okay, then what you do, you apply pre-compression and start increasing the pre-compression and see how failure looks like. So shear wall, if you have a shear wall, you can do this thing, pre-compression thing. But here in this case, there is some failure here. Some failure is, but it is converging. So there is a small failure. Okay. Okay. So it's, let's see what has happened. Stability failure is not very dominant. Why? Because what we did is we applied less level of pre-stress or pre-compression. Yeah, there's some failure. Okay, it failed very soon. So see, you just applied 30 megapascal pre-compression, and you could see hardening followed by softening. And obviously there is a stability failure has some role to play here. Buckling has some role. Mhm. Yes. So tomorrow we'll discuss cyclic loading. That is actually very important. It got also aborted because of the convergence issues. Okay, see. Actually, it failed very soon, right? Didn't it? See, it failed very soon. 1.17. No, sorry, this one. It failed at 1.97, right? Why did it fail? Because this increment was small. Then you have to go here, decrease this one, maybe 1 e raised to -10 or something like that, and then it will get completed. If not, then you have to maybe go. Then you have to go, like she said, general. I'll show you sometime else what to do here. You go general solution, select this one, this like this. I'll show it in future. You change the cutbacks here. That is one methodology, but let's not go there as of now. If I want to converge it, I think it will converge once I change the this step time. I decrease it. You can try it on your own also. If it still didn't converge, then we'll see what to do. Okay, I'll share this file with you. Tomorrow we'll go with uh, combined hardening and cyclic loading. Cyclic loading, for cyclic loading, we have to study kinematic. Have you studied kinematic and isotropic hardening? Anyone
No,
among you?
I'm
Don't worry, we'll
No.
discuss it. We'll discuss it. Briefly, but yes.
thank you very
Yesterday's
much.
class you haven't yet uploaded.
No, actually, what happened yesterday? No one joined.